Hi, in this video we're going to try to tie together the information that we've talked about basically so far in the course related to functions and use that to describe as completely as we can what's happening with the functions graph. Alright, so right here I'm going to just first of all summarize the key things that we know that can come from the original function f of x, the first derivative f prime of x, and the second derivative f double prime of x. All right, so when you're working with an original function, there's a lot of things that you could tell before you knew any calculus about the function. So some of those things are things like domain, maybe range. Range can be more difficult to tell depending on the function. So sometimes we need things like first or second derivative to tell about things like maximum or minimum values for a function, which would help us with range. We can tell from the original function things to do with x, y, input, output pairs, so coordinates of points. And then some things that we actually have done this semester, but that were with the original function before we talked about derivatives, are relevant limits. And while you can do lots of different limits with the function, the two important ones really are the end behavior. So limit as x approaches infinity of f of x, which will tell you what happens on the right side of the graph. Limit as x approaches negative infinity of f of x, which will tell you what happens on the left side of the graph, and maybe other limits as well. So I'll put here and others. And then one other thing, which I guess I would also put in the category of points, is one important kind of pair of points that you might find are x and y intercepts. So x-intercepts are where a graph crosses the x-axis. So if you just visualize that, points that are on the x-axis are going to have a y-coordinate of 0. So you can figure out the x-coordinate by substituting in y equals 0. And then the y-intercept would be where a graph crosses the y-axis. So that's going to have an x-coordinate of 0. So put in 0 for x and figure out what the y is. So all of those are things that really just come from the original function. There are probably some other things as well, but those are kind of the big deal things. From the first derivative, one important thing to remember is that the first derivative is always about slopes. So several key things that we have worked on really mostly in this chapter are things like critical points. Those are important because they are some of the possible locations of extrema. And so we often use critical points together with information about where a function is increasing and decreasing to determine whether we have extrema. So both local and absolute extrema. From the second derivative, remember that the second derivative is really about concavity. And so we find what we have been calling hypercritical points or hypercritical values. Our book does not use that. And then we can tell where the function is concave up or concave down. And if the hypercritical points are places where the concavity changes, then they are actually inflection points. And when we find things from the first and second derivative, sometimes we actually need y coordinates. So we might go back to just using an xy table from the original function to get input-output values, whether we're talking about extrema or inflection points. If we need y coordinates of those points, we're always going to go back to the original function for that, because that's really what the original function essentially is about: points, input-output values that are on the graph of the function. All right, so we're going to apply everything we can to completely describe the graph of this function here for an example. So I tried to pick a function that was not just a super simple basic function so that there would be some interesting things to talk about here. So certainly some of the problems in your homework are easier than this. But this one with the fraction exponent maybe has a little bit extra stuff to think about. There are lots of other examples. I could do an example that has a logarithm function in it, or a trig function, or an inverse trig function, or negative exponents, or all different kinds of things. So I want you to kind of focus on the big picture here and not necessarily just the details of this particular problem. But with that said, it is important to remember what x to the 1/3 means. That means the same thing as cube root of x, and then we have times x plus 4. When we do things like take a derivative or some other things perhaps, we might want to go ahead and distribute the x to the 1/3 through the terms in the parentheses here And so sometimes that's a little tricky for students to think about x to the 1/3 times x. So how you think about the algebra of that, x to the 1/3 times x to the 1, you're going to add those exponents. So 1/3 plus 1 is 1/3 plus 3/3, so x to the 4/3 plus 4x to the 1/3. So those are all just different ways that that original function might be written, and we might use different forms depending on what we're doing. But let's think about the things that we can tell about the graph of this function from just the original function. All right, so one of those things is about domain. So thinking about the domain of the function here, there is a radical, so there's something to think about there. But since this is a cube root, I can take the cube root of positive numbers, negative numbers, and 0 and get real valued outputs. If I had a square root, there would be some restrictions on the domain so that I don't get imaginary numbers for output values. But for this one, the domain is all real numbers, or negative infinity to infinity. The range is maybe a little bit more difficult to think about here. So we'll think about extrema, and that'll actually help us when we think about range. We can think about some relevant points. I'm just going to make a little XY chart over here. So some relevant points to think about might be x-intercepts and y-intercepts. X-intercepts occur on the x-axis, so the y-coordinate is 0. And so I'm going to put in y equals 0 and solve for x. So there's not a y here, but we know f of x equals y. So I'll have 0 equals cube root of x times x plus 4. I'm using that factored form because then it's a little bit easier. If I've got that equal to 0, I can then just set each factor equal to 0. And so when I solve this first one, cube both sides of this equation, I get x equals 0. And then here when I subtract 4, I get x equals negative 4. So I have two x-intercepts. I'm going to go ahead and put them in my xy chart over here. Y-intercepts, I actually already have that. It happened that one of the x-intercepts is also the y-intercept here, but I'm just going to write down a little bit here just in case you have a different problem where that's not the case. So when you do y-intercepts, you're going to be plugging in x equals 0 and find the y-coordinate that goes with that. Other relevant things to think about here would be limits. I can think about end behavior of the graph, so I can think about what happens as x grows large. So when I put in large values for x and then raise them to powers and add them together, it should be pretty clear that those y values are going to approach infinity. When I let x approach negative infinity, it's a little bit more subtle, and there's some stuff to kind of think about here. So I'm going to write these roots as powers. So this first term here, x to the 4/3, I can think about that as cube root of x to the 4th. Or if I simplify that, I can think about that as x times cube root of x, and then 4 times cube root of x. All right, so when I let x approach negative infinity, let's think about these cube roots here for a second. So these are going to get larger in size and stay negative. So both of these are going to approach negative infinity. And then the things that are times that, the x and the 4 is just going to stay 4. But this x that's here is also going to approach negative infinity. So this first term is going to approach positive infinity, and the second term is going to approach negative infinity. Technically, that's an indeterminate form, and you have to think a little bit harder about what's going to happen with that limit. But you should be able to see here that this first term is going to get so much bigger in size because this x that's out front gets so much bigger than the 4. Otherwise, those two terms are the same, except for the x and the 4. So when x is large in size but negative, this first term is going to dominate. And so because that first term approaches positive infinity, this overall function approaches positive infinity as well. All right, so we already have some pretty good information about the graph of this function. I've got a point at 0, 0. I've got another point at negative 4, 0. And I know that on both ends of the graph, the function goes up forever. The other thing that we might want to think about here, which I guess kind of crosses in between thinking about domain and limits, is continuity, thinking about where this function is continuous. We have a bunch of substitution shortcut theorems that are really about continuity. You might think about if you're taking the limit as x approaches a of any real number for x of this function, what would you do? And you can just use the substitution shortcut theorem on this. We have some about adding and multiplying by constants and rational exponents. So that's true for all values of a. So we also know that this function is continuous on negative infinity to infinity. So I know there are no breaks in the graph. All right, so if there are no breaks in the graph, and I know these points and that the right ends are up, then I have at least a kind of a rough sketch of the graph. We'll use some first derivative and second derivative information to help us find some more pieces of information about that graph. All right, I'm going to change colors here just to emphasize we're going on to something different here. We're going to look at the information that we can get from the first derivative. So I'm going to use the form of my original function where I had distributed through the 1/3 power. So I'm going to use this form for taking the derivative. So I'll bring down the exponent and subtract 1. Be careful with the fractions there as you subtract 1. So you have to be able to take that derivative correctly in order to do the rest of the stuff here. The other thing that you might want to do with this derivative, I especially do this when I have anything that's a little bit complicated, fraction or negative exponents, is that I will usually rewrite the expression as what that actually means, what those actually mean. It helps me think about the values for which the thing is undefined and stuff like that. So, all right, so I would probably rewrite this expression as 4/3 times cube root of x. And then the second term, because it's a negative exponent, I'm going to put that on the bottom. So 4/3 times cube root of x squared. So I've used a little exponent there, fraction, negative exponent, which hopefully you remember, but if not, just pause for a second there to be sure you understand why x to the negative 2/3 is cube root of x squared, but on the denominator. Okay, so we want to find critical points. Those would be where the first derivative does not exist. There actually is one of those here. It's hard to see when I write the f prime of x just the way I initially wrote it, but when you see it written with this denominator, where there's an x on the denominator there, you should be able to see that there is a point where the derivative does not exist. So that's a critical point. And then the other thing to think about here is where the first derivative is 0. So I'm going to set 0 equals the first derivative and solve for x. Again, I'm going to use the version that has the roots. I find that most students are a little bit more comfortable with roots than fraction exponents. But either way, if you handle the algebra correctly, you should be okay. All right, so this looks hard to solve. There's actually several ways to solve this. One way is to multiply through by the common denominator, or I'm actually going to use something else on this one because there's only 2 terms here. If I subtract one of the terms to the other side, so this last term here, if I just subtract it from both sides of the equation, I have negative 4/3 cube root of x squared equals, and then the term that's left, I'm going to rewrite that so that the variable is on the numerator there. So I've just used a little algebra to rewrite that. And then I can think about this like a proportion and just cross multiply here. So I will end up with negative 12 equals 12, and then I'll have cube root of x squared times cube root of x. So that'll give me cube root of x cubed, or just x. And nicely, that's simplified. So from here, the algebra is easy. All right, so sometimes students get overwhelmed because they can't see all the way to the end of how they would finish the problem, but I would encourage you to just do a step and see what happens. And in this one, after I did a step, now the rest of it turns out to be easy. That won't always be the case, but when it does happen, that's handy. Okay, so I have 2 critical points, one at x equals 0 and one at x equals -1. So those would be points that I actually probably want the y-coordinate of. So I'm going to scroll back up here. We actually already have one of them in my little table of values here. It was the x-intercept. But another point that would be relevant would be when x is -1. So I'm going to plug -1 into the original function and think about what the y-coordinate is there. So those are my critical points, and then the next thing that we usually do with critical points is we make a sign chart to determine where the function is increasing and decreasing, and that will also help us answer questions about extrema. All right, so -1 and 0 on my sign chart here, and then I'm going to check the sign of the first derivative. All right, so I'm looking at my first derivative in whatever form we want to do that. I'm going to use the one with the roots here and use that form. So when I plug in a negative number, like for example, x equals -8, I chose that because it's a perfect cube root. So when I plug in x equals -8 into my first derivative, it's maybe a little bit of work here to think about this, what you're going to get. So I'll have 4/3, and then cube root of -8 is -2, and then plus 4/3, and then cube root of -8 squared. So cube root of -8 is -2, and then when I square that, I'll get +4. So I don't really care so much about the number of the answer, but I do care that that's negative in that region. Okay, when I plug in a number between -1 and 0, you can certainly use your calculator to do this, but ideally, especially if you're going far in math, you'd want to be able to think about how to do these without necessarily needing a calculator. You may not always be allowed to use a calculator on things. So I would pick a fraction between -1 and 0 that is also a perfect cube root to plug in. When I plug that into that first derivative, I'll have 4/3. Cube root of -1/8 will be -1/2, and then 4/3 cube root of -1/8 squared. So -1/2 squared is +1/4. And then simplifying this, the key here is that this is positive. All right, and then when I plug in something bigger than 0, x equals 1 is easy. That one's pretty easy, maybe to just plug in, and you see that you end up with positive values there. Okay, so that's the sign of the first derivative, and that tells you that the function is decreasing, then increasing, then increasing. So we can say that the function is increasing on -1 to 0 and 0 to infinity, or actually I can go ahead and include 0 since 0 is in the domain of the function. So -1 to infinity, and decreasing on -infinity to -1. We also know that we have a local minimum at x equals -1. And since I already found the y coordinate of that point at x equals -1, I actually know what the local minimum value is. Let's go up here and combine that with some of the other information that we've got here. So I know the function is decreasing until x equals -1. And so I have a point down here at -1, -3. So decreasing until that point and then increasing after. And because of what I know about end behavior, I also know that that point at x equals -1 is going to have to be not just a local minimum, but also an absolute minimum when I combine the information I had with what I already know about the end behavior of the graph. All right, my picture here is not a great sketch of the graph yet. I've just kind of sketched in what I know about points and increasing, decreasing. I still need to think about concavity to make a little bit better graph. But notice I'm kind of just adding bits to the graph as I find out about it and refining my picture here. There is no local or absolute maximum on this graph. All right, and then the next thing that I can find is information from the second derivative. And again, I'm going to rewrite this in terms of what it means to help me think about values where this derivative maybe does not exist. Okay, so thinking about hypercritical values, so places where the second derivative does not exist at x equals 0. And then thinking about when the second derivative is equal to 0. So I'm going to put 0 in for the second derivative and then solve for x. And so I'm going to use that same trick that I used before, just move one term to the other side. And then I'm going to cross multiply. All right, I'm going to notice that with my coefficients here, if I divide through by 36, that simplifies the coefficients. Okay, you want to be careful here about dividing through by x. You can actually get away with that on this problem, but in general, you want to be careful about dividing through by variables. And instead, when you're tempted to divide through by variables, add or subtract terms to one side and factor out instead. All right, so I'm going to subtract the cube root of x to the 5th from both sides of the equation. And then I'm also going to do a little bit of factoring, and there's several ways to think about this, but I'm going to write it out this way. And again, if your algebra skills are awesome, maybe this is easier for you than if your algebra skills are a little weak, but it's okay if they're a little weak. Just pay attention to what we're doing here. I can think about cube root of x to the fifth and simplify that by thinking about that as cube root of 5 x's. They're all times each other. Right? And then cube root of this x cubed is just x. Cube root of that x cubed, that group of 3 x's that are there. And then I'm left with, inside the radical, this group of 2 x's that's not a perfect cube. And the reason I did that is because then you can see you have a common factor of cube root of x squared that you can factor out. And then you can set each factor equal to 0. All right, so from this first one, if I cube both sides and then square root both sides of this equation, I'll get x equals 0, which actually is not in the domain of the second derivative. If you go back up here and look at the denominator, we actually already had that as a hypercritical value, though, from when we looked at when the second derivative does not exist. And then this second one, I'll get x equals 2. So I have 2 hypercritical values, one at x equals 0 and one at x equals 2. And so let's put those on a number line and check about concave up and concave down. All right, so I want to look at the sign of the second derivative. So I'm going to plug some numbers into that second derivative. Let me zoom out here so we can see everything all at once here. All right, so second derivative, and you can use whichever form you want. I'm going to go ahead and use this form that has the radicals here. And again, I'm going to pick some things that are perfect cubes to plug in. So when I plug in something left of 0, a perfect cube that's left of 0 would be something like x equals -1. And I'm going to plug that into the second derivative. You should be able to see that you're going to get 4/9 minus negative, so plus 8/9. And the key there is that that second derivative is positive. Something between x equals 0 and x equals 2, like x equals 1. Which is negative. And then something bigger than 2, like x equals 8. All right, and so you can simplify these a little bit. I'm going to notice that 8 goes into both 8 and 32, and so that way both fractions have a denominator of 36. So I have 436 minus 136, which is positive. So the function is concave up on 2 different intervals. Concave down on the interval 0 to 2. And I have an inflection point, 2 of them, one at x equals 0 and one at x equals 2. And so to find the y-coordinate, I'm going to go back up to my original function and my little table of values and find the y-coordinates for those points. All right, so I already have the one at x equals 0, and then I don't really have room in my chart there, so I'll just make another one over here to plug in x equals 2 to the function. All right, when I plug in x equals 2, it's not quite as simple as some of these other ones turned out to be. I'm going to just use the original expression for the function, or maybe the one with the cube root. When I plug in x equals 2, inside the parentheses I'll have 6, but then times cube root of 2. So if I want to leave that in exact form, that would be the ordered pair 2 comma 6 cube root of 2. Okay, so at this point we are ready to tie all of the information together that we have found so far and sketch a complete and correct graph of the function, and then I'm going to check that on Desmos. So I had a pretty good sketch here already. The new information that I have here is about concavity. So the information that I found says that the function is concave up on -infinity to 0. So this part of the graph here, until I get to 0, should be concave up. I almost had it that way in my sketch already. And then the other part of the function that's concave up is to the right of x equals 2. So there's an inflection point here at x equals 2 comma y equals 6 times cube root of 2. I might want to get a decimal approximation for that to help me. But I also know that in that part of the graph, the function is concave up over there. That we probably would not have known if I hadn't done second derivative. And then concave down between x equals 0 and x equals 2. So concave up, then concave down, then concave up again, and I have an inflection point at x equals 2. All right, so that's not a great sketch. If I was going to make a better sketch of that, I really should scale off my axes properly so that I don't just have points labeled as -4 and +2 and -3 here, but have a reasonable scale here. And then at that point, I'd probably want a decimal approximation for 6 times cube root of 2. It's a little bit bigger than 7, between 7 and 8. All right, so roughly, using the information that we have, got a point at the origin here, concave up, concave down, and then concave up again. And maybe I want to label these points 2, 6 cube root of 2. I've got another important point here at the origin, 0, 0. Another important point here, -1, -3. And an important point here, -4, 0. All right, so there's a sketch that I did by hand, just using all the first and second derivative information. I also have Desmos ready here. So here is the function graph when I just graphed it on Desmos in the window it started with. And you can see that what I sketched looks pretty good. What you can't really see on Desmos is the concavity change at x equals 2. So if I just look on the screen here, there is a point at x equals 2. If I click on that, Desmos is going to give me an approximation for that point right there. So it's hard to see from the graph, though, the concavity change as you go from the right of x equals 2. And even if you zoom out or change the viewing window, it can be difficult to see that change in concavity. So I want to emphasize that that's really what the power of calculus gives you, is that you have great graphing tools, graphing calculator or Desmos or whatever, that can get a pretty complete graph. But sometimes there are things you can't see just from looking at it. I can see on here the local minimum and the concavity on most of the graph. The thing that is difficult to see from just looking at it, though, is the concavity change that happens at x equals 2. It's a very slight change, and unless you really examine the graph closely and look at points carefully, you probably can't tell what's happening there with that change in concavity at x equals 2. All right, so try some homework problems.